Okay, so this is our last video. We're going to do a review like we used to do in class right before a big test. This is going to cover everything that we would be reviewing at the end of the year before you take the Regents exam. So going back all the way to the beginning of the year, we started with measurement and estimations. So the thing with measurement was being able to convert, right, using those prefixes on the front of your reference table for the metric system, converting from centimeters to meters, grams to kilograms, hours to seconds, right, any of those. The other thing was estimations. So estimating the length or the height or the mass of different things. These are typical questions that you will see, right? Estimate the length of a football field or the height of a doorknob above the floor. Maybe estimate the mass of a nickel or a chicken egg. And you're going to estimate to the closest power of 10, right? The closest order of magnitude based on the unit that's given. Right? So typically you're estimating in the base units, meters, kilograms, right? Things like that. Then we started to get right into kinematics. So we started with 1D motion, right? So a couple of things we defined right off the bat, distance versus displacement, right? So remember here, distance is the total path that you travel, including every step, going backwards, right? Displacement, however, is the shortest path from start to finish. So this is essentially your straight line. So if you were to start here and walk north and then east and then south, and end here, right? So you start at 1, you end at 2. Your distance is the whole path, but your displacement would just be the shortest distance from 1 to 2. Okay. Then we talked about speed versus velocity. So here's where we started to get into some of our equations, right? So speed versus velocity. Speed uses the distance, velocity uses displacement. Okay? However, the relationship for both of them is v equals d over t. And then you have to know what to plug in for d. Right? The units for this are meters per second. Okay? Then we talked about scalar versus vector. So scalar quantities have only magnitude, so only the number, right? Just the size. A vector has magnitude and direction. So every quantity we talked about this year can be classified as either a scalar or a vector. So if we just go back here, distance is a scalar, displacement is a vector. Speed is a scalar, right? S for scalar, S for speed. V for velocity, V for vector. Velocity is a vector. Okay, so you need to include the direction here. So velocity would be something like 25 meters per second north, right? Whereas your speed would just be 25 meters per second. Then we talked about the acceleration, which is a change in your velocity. So acceleration is change in velocity over time. Now remember that this change in velocity is final minus initial, right? You're looking at the difference between your velocities. And then units for this are meters per second squared, and this is a vector quantity, right? Because it uses velocity, and velocity is a vector. So acceleration is also a vector. And then we had more equations that we looked at and derived together. So if I just take the acceleration equation and solve for VF, I get VF equals VI plus AT. And then combining that with V equals D over T and looking at the average velocity, we have VF squared equals VI squared plus 2AD. And the distance equation, D equals VIT plus 1/2 AT squared, right? All of those are on your reference table. So that was basic 1D horizontal motion, right? Then we started talking about motion graphs. So motion graphs got into looking at how objects are moving, right? And so the first things we looked at were distance versus time graphs. And so the distance versus time, the slope, change in y over change in x, would be meters. Remember, for the slope, we look at units, meters per second. And that gives us, meters per second, is the speed or the velocity. Right, so the slope represents speed or velocity. And then again, we look at the shape of the slope. So this graph is showing you an object that is not moving, right? The slope of this is 0, so that means the speed is 0. The graph here in the middle where I have this nice increasing line, it's a straight line, so it's constant, and it's an increasing line, so this is showing you something that is traveling at a constant speed. Right? Straight line means constant, the slope represents speed, and then I have a curve. So this is a changing speed, and we know that changing speed means that something's accelerating. Okay, the area of a distance versus time graph. If I took the area of this, I'd be multiplying distance times time, so meters times seconds. That doesn't tell us anything. If we go to velocity versus time graphs, right, let's analyze the slope. So I'm going to look at my units here. So I have meters per second and then time. So if I analyze the slope, change in y over change in x, meters per second, which is meters per second squared. So the slope here tells me the acceleration. Okay. So here, straight line, flat line has a slope of 0, so my acceleration is 0, which means constant speed. Okay. Here I have a straight line again, but it's an increasing line, so this is going to tell me constant acceleration. And then here I have a curve, so this is a changing acceleration. This is something you don't see too often, right? But this is a changing acceleration, right? Or non-uniform acceleration, we should say. And then if I look at the area, so if I were to just draw a section here, let's look at the area under the curve. To find the area of this, we are going to do essentially base times height, but I'm going to look at just my units here. So I have meters per second times a second, so this will cancel, and I'm left with meters. So that tells me that the area under the curve represents the distance or the displacement. Okay, good things to know there. Then we talked about vectors. Right, so let's start up here with vectors. So we talked about vectors and drawing vectors. Remember, a vector has a tip, which is the arrowhead, and a tail. Vectors represent magnitude and direction, right? So the magnitude is how long you're drawing this, so you have to use a ruler. And the direction has to do with, the angle at which you're drawing the arrowhead, right? To solve vector problems using vector addition, this is where our vector diagrams come in. So you want to make sure you draw everything tip to tail. So if we take a journey and we walk, let's say, 2 meters north and 1 meter east, I could find the resultant between those two vectors, right, which would give me this red vector value. And then, of course, I could use some trig, SOHCAHTOA, to find the angle. So we did lots of that because that comes into play with a lot of the units that we looked at, including projectiles and riverboat problems and forces. Okay. The other thing to remember about vectors is they have two components, right? Every single vector can be broken down into its components. So if I just have this random vector here, I can break this into its two components, right? And so here would be vector in the x direction, that component in the x direction, and here would be my vector in the y direction. So if I call this original solid line vector v, right, we could come up with relationships here. So in the x direction, here's my angle. This is my adjacent side, so this would be v times the cosine of theta, right? So the magnitude of the actual vector times the cosine of the angle, and then vy would be v times the sine of theta. Right? And we derived those together. So we did lots of things with vectors. Okay. Then we got into free fall. So when we're talking about free fall, we're still looking at one-dimensional motion, but now it's in the y plane, right? So vertical. So we know that things fall down due to gravity. So things will accelerate down due to gravity, and we made this a negative value to indicate the downward direction. So remember, our coordinate system here is saying anything up is positive, down is negative, right is positive, and left is negative. Right? So the definition of free fall is that the initial velocity is 0, and then we know that as this leaves, it's going to accelerate downward, which means the velocity of it is going to increase. So the distance it travels will increase, right? So each consecutive distance gets larger. And then finally, I kind of ran out of room down here, we have the final velocity when it hits the ground. And we call this the impact speed. So remember that that is not 0. You can actually determine how fast it's traveling when it hits the ground. Okay? And so for this, we used our same equations on the reference table. Distance equation came into play a lot, but the thing that I'd like to draw your attention to is that initial velocity is always 0. So really, when you use the distance equation for free fall, you're just using d equals 1/2 at squared. Okay? So after free fall, again, things to take note of: the distance here. As this falls, the velocity is increasing. Right? It starts at 0 and then it has some velocity when it hits the ground. So then we're over talking about some of our vertical motion. Right? So vertical motion, now you have your initial velocity has to be greater than 0 because you want this to go up. So as it goes up, notice that the distance it travels is pretty large, and then that gets smaller and smaller and smaller because as it travels up, the velocity is decreasing. And then it gets to the peak up here where the velocity is 0. Remember, it has to stop for a split second, but the acceleration is still negative 9.81. So that's a unique moment in time where you have a velocity of 0, but an acceleration that is not 0, right? Because it's turning around, it's changing direction. So the thing to remember here is that what goes up must come down. So on the way down here, this right-hand side will be free fall. So everything you know about free fall. But on the left-hand side here, this is vertical, right? So throwing things into the air. If this is a level-to-level problem, the final velocity that this lands back on the ground with will equal the initial velocity, but just in the opposite direction. So we say negative of that. Right? If I were to graph this motion, velocity versus time, for throwing something straight up into the air, as it goes up, the velocity decreases. And notice my initial velocity is greater than 0. So here's 0. That means I'm going to start up here somewhere. Right? So it's going to 0. So this is the peak where the velocity is 0. And now it turns around and comes back down. But it has a negative velocity because it's coming downward. That's an important graph. Then we combine things and we started talking about 2D motion, projectiles, my absolute favorite unit. So remember, with projectiles, we're launching or throwing or kicking something at an angle. So we'll call this theta. And the very first thing you have to do is break this vector into its x and y components. So that's why we spent so much time talking about vectors. Here's where we created our xy chart. So you have initial velocity in the x direction, initial velocity in the y direction. Okay, and those equations we derived together. So this would be vi times the cosine of theta, right, because this is my adjacent side. And this would be vi times the sine of theta. Okay. For every single projectile problem, acceleration in the x direction is 0, right? And the acceleration in the y direction is due to gravity, so negative 9.81 meters per second squared. Okay. Remember, we made this chart, this xy chart, because you want to work in the x and y plane. So you have a distance in the y direction, that would be your maximum height, dy. So you could find how high this goes. You have dx, the distance in the x direction, the range. And then we also found time, typically. So we found the time to the peak. Remember, at the peak up here, your velocity in the y direction becomes 0. Right? And so this is only at the peak. And then it's going to turn around and pick up speed again. So we found the time to go up, right, by using kinematics equations. And then we doubled it because we know that the time to go up equals the time to come down. Right? Again, as long as it's level to level. And then we used the total time to find the range. The other thing to remember with projectiles are these angle relationships. So remember that 45 degrees was a very unique angle at which to launch a projectile. So as you change the angle, you are going to change a few things. So here's my object. If I launch this at a pretty low angle, right, it'll go up and come down. If I increase this angle, it'll go higher and further. And then if I continue to increase beyond 45, yeah, it'll go higher, but the range will start to decrease again. Right? So as you increase from 0 to 45 degrees, the distance in the x direction increases. The distance in the y direction, the height, increases, and the time in the air also increases. As you increase the angle from 45 degrees to 90, now your distance in the x direction starts to decrease. Right? If you launch it at 90 degrees, your range will be 0. It'll go straight up and straight down. Right? Distance in the y continues to increase, and time also continues to increase. So 90-degree launch angle will have the highest height and the longest time in the air. 45-degree launch angle will have the longest range, distance in the x. And the last thing here is to remember that complementary angles, right, add to 90, are going to land in the same spot. The next thing that we're going to look at here is impulse and momentum, right? And so I think we actually did a little bit of forces before we did this, but we're going to look at impulse and momentum because this is still kinematics, really. So impulse and momentum. Remember, any moving object has momentum, right? So momentum, P equals mv. And we know that when you want to change the momentum of an object, essentially what you're doing is changing the velocity, right? You're not going to change the mass. So when you change the velocity, that means that you have something that's accelerating. And we know from Newton's laws that when things accelerate, there's a force that's causing that to happen. So we have the mass times acceleration, right? That's your net force. And putting this together, we came up with FATMAV. So FATMAV is a really important relationship, right? Again, something that's not on your reference table, but hopefully you added it there, where the impulse is equal to the change in momentum. Right? So impulse is J equals F times T, and you have this equation that is on your reference table. Impulse equals the change in momentum. So the thing to remember with impulse and change in momentum is this fact here. The force felt by each particle, right? So for instance, if you have the example of the bug hitting the bus, right, on the windshield, each object feels the same force. So the bug experiences a force and the bus experiences the same force because they are experiencing the same impulse. However, the difference that you notice between what happens to the bug and happens to the bus occurs because of their change in mass, the difference in their mass. So the impulse is the same for both, right? This side of the equation is constant, which means this side of the equation has to be different because the bug has a different mass than the bus. So if you have a small massed object, that means the change in velocity will be very drastic. So the bug has a very small mass. At one point he was flying, let's say, to the right. He hits the windshield of the bus and now he's flying to the left. So because he's on the windshield. So it's a very drastic change in velocity. Literally changes direction. Right? On the other hand, the mass of the bus is very large, so its change in velocity will be very small. Right? The bus does not feel the impact of that force from the bug to change its velocity really at all. And then the big thing with momentum was conservation, right? And so we saw that we did that collisions lab where you had conservation of momentum, where momentum really is transferred between objects. Okay? We also looked at collisions versus explosions, so that was also in here a little bit as well. So we had collisions where two objects collide and maybe they bounce off of each other, or maybe two objects collide and stick together. And then we also looked at explosions, right, where your initial momentum was 0, and then your final momentum was also 0, but that's because you had pieces flying in different directions. Okay. Then we talked about forces. So now we'll get into forces. The first things were Newton's laws. Number 1 is the law of inertia. An object at rest wants to stay at rest, an object in motion wants to stay in motion unless acted upon by a net force. Law 2 was F net equals ma. So a net force causes an object to accelerate. And then law 3 is your action-reaction forces come in pairs. Right? So if I push on you with 20 newtons, you push on me with 20 newtons. So the thing to remember about F net, there's 2 ways to determine the net force. You can use F net equals ma, or you could use F net as being the sum of the forces where you're using vector addition. So if we just look at a table and we put a box on a table, we know that this box is going to experience a few forces. We have Fg, right? The force of gravity pulling this down. So remember Fg equals mg. And then we also have the normal force pushing back up. If that box is at rest, that means it's in equilibrium. So when F net is equal to 0, that means your object is in equilibrium. Right? So the acceleration is 0, which means that the sum of my forces has to be equal to 0. So Fn plus Fg, or really minus Fg, because they're in opposite directions, must equal 0. Right? So this is the one people always forget, how to find net force. You can add your forces together. But again, remember, we have this coordinate system where anything up is positive and down is negative. So since these point in opposite directions, I'm going to use vector addition and subtract them. We then talked about the force of friction. So you have static friction versus kinetic friction. Remember, static friction is when things are stationary. Right? And static friction, here's the key with static friction, it can build. It builds. Right? It gets stronger and stronger and stronger. There is a maximum static friction that exists between the materials. And then once you overcome that static friction, now you've set your object in motion, and so you have kinetic friction. So this is when things are moving. Remember that static friction is always larger than kinetic. Right? It is easier to keep something moving than it is to set it in motion. Right? That goes back to Newton's first law. An object in motion wants to stay in motion, and an object at rest wants to stay at rest. Okay. Here's your friction equation, right? So remember your coefficient of friction, that is a unitless value. It depends on the materials that are touching, so you have that chart on your reference table. And then Fn, remember this is the normal force, the surface pushing back. Right? A lot of people get this confused with net force, so just beware of that. Then we got into inclined planes, right? And so this is where the normal force becomes really important because it's off at a different angle. So what we've done here is tilt our coordinate system. So anything kind of down the incline, right? That angle of the incline is positive, up is positive towards that normal force. This will be negative, and then up the incline will be negative. So you'll notice that my Fg vector does not fall in this coordinate system anymore. So we break that into its components. Right? Here's a right angle, and this angle up here is the same as the angle of the incline. Right? We went through that in class. So we have Fg that's perpendicular to the surface and Fg that's parallel, and we calculated those. So Fg perpendicular, right? If this is a right triangle, that'll be equal to Fg times the cosine of theta. Remember, Fg is mg. And then Fg parallel, that pulls down the incline, is Fg times the sine of theta. Okay. The reason this is really important, if I break the gravity vector into its components, it's like that's gone. So I have Fn and then these two red vectors. And if that box is just going to slide down the incline, Fn has to be equal to Fg perpendicular. Very, very important. So if this is frictionless, so if we have a frictionless incline, the net force will be equal to Fg parallel. Right? So essentially this is m times g times the sine of theta. Right? Because these two forces cancel. If there is friction, that means we have to add a friction vector going up the incline. So if it's moving, actually let's do static friction first. So if we're looking at the force of static friction, that means my net force will be equal to 0, right? If this is not moving, if it's stationary. So that tells me that force of friction static will equal Fg parallel. If we get this to move, so now we're looking at kinetic friction, that means that my net force will be the sum of Fg parallel and force of kinetic friction. So this will be Fg parallel minus the force of kinetic friction. Right? Inclines were fun. And then to round out forces, we have gravitation and circular motion. Right? So gravitation was essentially Newton's fourth law, right? Where we know that all objects attract each other with mass. So here is our universal gravitational equation, Fg equals capital G, m1, m2 over r squared. This is where acceleration due to gravity comes from, right? So if I look at that equation, I'm going to look at two objects, the Earth and me. I'm standing on the Earth. So I have capital G, the mass of me times the mass of the Earth, over the distance between us, which really is just the radius of the Earth, right? And I'm also going to look at the only forces acting on us are F equals ma, right? So my force, my net force, is my mass times my acceleration, and I want to solve for this. So I'm really just going to set these two things equal, right? So ma equals g little m big M over r squared. Substitute, rearrange, and I get 9.82, right? Which is roughly little g, right? So that's just where this comes from. Good to know. The other thing, this is an inverse square relationship, right? This is a squared value. So you need to know what these graphs would look like. So as the distance between these objects increases, the force decreases exponentially. So you have something that looks like this. The other thing that we talked about when we talked about gravitation was Kepler's laws, right? So Kepler's laws, planetary motion, that's something else that goes kind of along with gravitation. And Kepler had 3 laws, right? The first was elliptical orbits with the sun as one focus. The second law was equal area in equal time, right? And that's the one where we drew a picture. So if here's my sun and my orbit, as the planet moves from one location to another, if we draw imaginary lines, it's going to sweep out this area. And then over here, again, if I draw imaginary lines, in the same amount of time, it's going to sweep out the same area. Okay. Law number 3 was the period and distance relationship, right? And I told you you wouldn't really ever have to use that, so I'm not even going to put that in here. And then finally, to round out forces, we talked about circular motion. So remember, any object traveling in a circle has a force acting on it because it's constantly accelerating since it's constantly changing direction. Right? So remember, velocity is tangent to the circle. The acceleration is towards the center, so we call that centripetal acceleration, center seeking. And then the force is also towards the center. To find the velocity of something moving in a circle, still using v equals d over t, but the distance of something moving in a circle is the circumference. So 2 pi r over capital T, this is the period, time for one revolution. Okay. Centripetal acceleration is v squared over r, and then using Newton's second law, F equals ma, we just substitute in. Now, something really important. Centripetal force, it's not a different force, right? It's not a new force. It comes from something else that we talked about in the forces unit. It comes from friction, right? When you turn and drive around a curve in your car. It can come from tension if you're whipping something around on a string. It can come from the normal force. It could also come from gravitation, right? So gravity could provide that centripetal force if this is, if we're looking at planetary motion, right? And so Fg would be equal to Fc, right? So it's not a new force. You have to figure out where the centripetal force is actually coming from. Okay. Then we got into energy. So that was our forces unit. So then we talked about energy and work, right? So different types of energy, potential energy due to gravity, right? These equations are on your reference table. So this is mgh, potential energy due to a spring, 1/2 kx squared. So remember, x is the distance of compression or stretch. And then kinetic energy is energy of motion, 1/2 mv squared. The big thing with energy and work is that your change in energy is equal to the amount of work done on the system, right? So this gets into then conservation. So energy is always conserved. It changes form. So it can go from potential into kinetic or from potential into kinetic plus heat, right? So you'll just have this transfer of energy from one form to another. So one of the examples we did in class was this bowling ball pendulum, right? Right now it has no energy. If I do work on it and lift it to some height above equilibrium, actually, this would be my equilibrium, excuse me, sorry. Right, here's equilibrium. This is the height above the ground, which we don't measure. So height above equilibrium here. Okay. Now this has potential energy. If I let it go, and now it's swinging, it's going to get a little bit lower, little whoosh lines behind it. Now it's swinging, so it's still some height above equilibrium. Here it will have potential plus kinetic. Swings through equilibrium where it has only kinetic because it's no height above equilibrium. It will go back up, continuing to swing, and then it finally will reach a height where it only has potential, right? And these two heights will be equal if this is frictionless. So you see that transfer of energy there. If we add friction in, remember there was tons of friction at that pivot point hooked at the ceiling, and friction with the air molecules. That means it will start with some potential. At this point, I'll have potential plus kinetic plus anything that's coming out due to Q, heat, friction. Here it will have kinetic plus Q. Here it will have potential plus kinetic plus anything lost to heat. And here it will have potential plus Q. So this height will be a little bit less than the original, right? So it won't get as high if we're considering friction. The other thing to remember with work, right? Work done is the change in energy, but for work to be done, really, the force and the displacement of the object must be in the same direction, right? So this is the equation that's on your reference table, W equals FD. For some of us, we looked at W equals FD times the cosine of theta because you want to find the component of the force that's working in the same direction as the distance. Right? So some of us have used cosine of theta, some of us have not, right? So that's up to you. And then, of course, as I talked about, Q is heat. That accounts for any quote-unquote missing energy. It's really not missing, it just has changed form into heat due to friction. And that was really the first half of the year. That was all the kinematics. So then we got into electrostatics. Right? So electrostatics is static electricity. So we talked about how there are two charges, right? Positive and negative. And like charges will repel, opposite charges will attract. Remember that this positive and negative charge comes from a transfer of electrons. So if something is positive, that means it loses electrons. If something is negative, it's gaining electrons. Really important. The other thing that's really super important is that if something is neutral, it will attract to either charge. So to prove that something has a positive charge, it must repel from another positive charge. To prove something is negative, it must repel from something else that's negative. Okay. Charge is also conserved, right? So if a balloon gains 10 electrons, that's because hair lost 10 electrons when you charge through friction. One elementary particle, right? So for instance, one electron has a charge of 1.6 times 10 to the negative 19 coulombs. We would make that negative since we know electrons are negative. Proton has the same charge, but it's positive. Okay? And then I gave you this relationship that comes from this conversion up here, right? But the total charge on an object is equal to the number of particles it has either gained or lost times the charge per particle. So 1.6 times 10 to the negative 19 coulombs. Right? And that leads us into Coulomb's law. So Coulomb's law looks very similar to law of gravitation. So you have F equals K, which is a constant, charge 1, charge 2 over the distance squared between them. Right? So again, this is an inverse squared relationship. So as the distance between these increases, the force will decrease exponentially. Right? So you should be able to look at those graphs. Okay. Then we started talking about the electric field. So if we add the electric field over here and electric field lines, right? So the electric field is the space around a charge. Remember, when you charge something, you're changing the physical space. So around a positive charge, when we draw the electric field lines, remember the field lines show us how a positive particle would move. So positive would be pushed away from a positive. Right? So those field lines show us how positive particles would move. Right? So lines indicate a positive charge, right? How a positive charge would move in that space. Okay. We calculated the strength of the field just briefly. So to determine the strength of the electric field, this is equal to the force felt per the charge. Right? So that's your electric field equation. And then the other thing we also looked at was the potential. So if you take a positive charge and you actually move it closer to that positive source charge, you know they don't want to be close together. So you're actually increasing the amount of potential. And that has to do with the amount of work you do over the charge of that object. Right, good things there. Then we talked about how to charge things, right? So you can charge things through friction, just literally rubbing them together, right? And you're going to transfer electrons, right, physically from one object to another. You can charge by conduction, is when you touch objects together. And when you charge by conduction, you get the same charged objects. We charged by induction, which was through grounding, right? So you ground the object, and when you do that, right, you're touching with your finger, and you get opposite charged objects. We also looked at the electroscope, right? So remember the electroscope, the leaves are what you're interested in. So if this is a, let's just say it's neutral, right? So we'll just have it be neutral. If I charge it, some charge, right? Let's say I give it extra electrons, that means the leaves are going to become more negative and they're going to repel one another. So if I just give this a few more electrons, right, than protons, it has an overall negative charge. So those leaves are going to repel. Right? And so we looked at those a little bit. Right. Then we got into electricity. So we know that electricity, we're going to follow the flow of electrons, right? And the current, the flow of those electrons, is the charge per time. Current is measured in amps. Right? So capital A, that's your unit. The other thing we looked at was the potential difference, right? So essentially this has to do with the amount of potential energy that your charges have. And we're using Ohm's law to look at that. So V equals IR. And then resistance, right? Resistance is something that you need in a circuit in order for you to build a working circuit. Otherwise, you don't have something that's going to use the energy, and that creates a short circuit. Right? The other thing we quickly looked at was the resistance of a wire itself. So remember, that has to do with the resistivity. Right? This is the resistivity, and that depends on the material. Okay? You have a chart of resistivities on your reference table. But the resistance is directly related to the length and inversely related to the cross-sectional area. So something that is long and skinny will have a very high resistance. Something that is fat and short will have a very low resistance. Easier for you to crawl through something that's wide open and not very long. Much harder for you to crawl something that is very, very small, area-wise, but long. And then we got into series versus parallel circuits. So series circuit has one path. All of your electrons must go through each resistor. So remember, electrons leave this short end, the negative side of the battery. They have to go through R1, R2, and R3. So the current is the same everywhere. The total resistance, since we're going through all three of them, is the sum of those. And the potential given by the battery, this is V total, will equal the potential used at resistor 1, the potential used at resistor 2, plus the potential used at resistor 3. Right? So again, that's the sum. When you add more resistors in series, your total resistance will increase. Then we're into parallel circuits. Right? So a parallel circuit looks like this. Again, we can follow the flow of electrons. And now here's where we have branches. So you have points on your circuit where current is going to split. So some of this current will go through R1 and then back to the battery. Right? So whatever potential was given by the battery must be used in V1. So for parallel circuits, V total equals V1 equals V2 equals V3. The total current is the sum of the current through each branch. And then this is the weird one, right? Total resistance is 1 over total resistance equals 1 over R1 plus 1 over R2 plus 1 over R3. So as you add more resistors in parallel, the total resistance actually decreases. And this example, a great example of this, is the toll booth analogy. Right? So remember, when you get on or off a highway, you have to go through a toll booth. I totally spelled this wrong, right? You have to go through a toll booth. And the more toll booths that they have open, the more choices you have, right? So the more branches you have, the more choices you have, and traffic just flows. Remember that we can use Ohm's law in a series or a parallel circuit for the circuit as a whole, or for each individual device, right? So V total equals I total times R total, or V1 equals I1 times R1, so on and so forth. Right? And then we briefly looked at power and energy in circuits, and those equations are on your reference table. Okay. Then we got into magnetism, and magnetism is where we started this remote learning. So you watched videos on magnetism. We had left-hand rules on magnetism. There's not too much that the Regents exam actually requires you to know about magnetism, right? But you should know that magnets have two poles, north and south. Like poles repel, opposites attract, and the Earth is essentially a magnet itself. So the liquid iron core creates that, and geographic north, what we know as the North Pole, is actually a south pole of a magnet, which is why compass needles point north, because this is a north end of a magnet, and we know that a north will attract to a south. Okay. When you draw magnetic field lines point out of the north and into the south. Right. So again, you imagine placing a little compass needle around that. It's going to point towards the south pole. Current carrying wires are something that you should be aware of as well. So when current is sent through a wire, there's a magnetic field that gets created around the wire, right? This is electromagnetism. This was left-hand rule number 1. So my thumb goes in the direction of current, my fingers curl around, right? And so I have this field that's going to go around the wire this way, right? Up in front. But what you should know is that you get this circular magnetic field around the wire. And that leads us into the motor principle, right? So when you place a current carrying wire in an external magnetic field, you get this motor principle, which where you have these interacting magnetic fields, right? Motors and generators operate that way. Right? So there was more in magnetism that we looked at, but that's really all that you need to be aware of. Right? And then waves. So we got into waves. We talked about periodic versus a pulse. So pulse is one disturbance. A periodic wave is multiple, right, at timed intervals. And then we talked also about transverse versus longitudinal. So a transverse wave looks like a sine curve, right? And this is where your disturbance is perpendicular to the direction of wave travel. Longitudinal, the disturbance is parallel to the direction of wave travel. So longitudinal, the best way to look at this is to think of air particles, right? And when sound travels through air, or you could think of a slinky, right, pulling the coils back of a slinky. But if my wave travels to the right, the particles are going to move to the right as well. Right? And so the particles you can see are moving to the right to kind of condense in certain areas. So disturbance is parallel. The thing to know here, light is a transverse wave, sound is longitudinal. Then we talked about characteristics of waves. So the frequency, how often it repeats itself, the amplitude, which is essentially the height, right? So the amplitude is how high from equilibrium. The period is the time for one cycle. So period and frequency are related, right? Where the period is equal to 1 over the frequency. The wavelength is the distance from 2 points in phase. Right, so this would be 1 wavelength. The speed of a wave, v equals f lambda, so the frequency times the wavelength. And then we talked about interference, constructive versus destructive, and reflection. Okay. The next thing was really standing waves, right? So creating a periodic wave that interferes with its own reflection, and this is what you would see. Right, so I'm sending a wave down and it's reflecting back, and notice that the reflection is the opposite, so my reflection is a dotted line. And then we had nodes where we had points of destructive interference, and antinodes where you had points of constructive interference. Right, so nodes are points that have no disturbance. Antinodes are points that have maximum disturbance. Right. We quickly looked at musical instruments and creating resonance in musical instruments with standing waves. So this term resonance is when you match the natural frequency of a material and cause that material to vibrate. Right. So examples of this, an opera singer that shatters a glass or a mirror, right, singing a certain frequency note. The Tacoma Narrows Bridge that collapsed because the frequency of the wind matched the frequency of the bridge. Or pumping your legs on a swing, right? You match the frequency of the length of the swing. Okay. And then we have our musical instruments, right? So just something to be aware of, drawing these standing waves in your musical instruments. Okay. Then we talked about diffraction of waves. So the spreading of a wave beyond a barrier, right? So waves can diffract. So if I have this wave that's coming in, it's going to hit a barrier, kind of like a picket fence, right? And as it goes through this, it's going to diffract and bend and change shape as it spreads beyond the barrier. Okay? This is something unique that waves can do, right? Particles cannot do this. So this is unique to waves. And this is one of the reasons we know that light travels as a wave, because it can diffract. Okay. And then we got into light specifically. So you have your electromagnetic spectrum. These are all light waves, and they all travel at the speed of light, c. So 3 times 10 to the 8 meters per second. Right? You have that on your reference table. Okay. Snell's law has to do with the bending of light. And here's Snell's law equation, again on your reference table. But this is the bending of light as it travels into new media. Right? And that has to do with the index of refraction. So the index of refraction, n, has to do with the medium that the light is traveling into, and it's a ratio of the speed of the wave in a vacuum, 3 times 10 to the 8, divided by the speed of the wave in that material. Right? So a larger n value means that the speed is going to be slower. So remember that light is going to come in and be incident on this boundary. Right? Let's say that this is air, and then let's say we're going into glass. And we know that as light goes from air to glass, glass is more dense, it will have a higher n value, so it's going to slow down, which means it will bend. Instead of going straight through, it's going to bend towards the normal. Right? That's very exaggerated to show you that. So those are things you should know. When light bends away from the normal, it is going to speed up. When it bends towards the normal, it is going to slow down. So you should be able to look at a diagram and just see what's happening. So this is getting closer to the normal line, so it's slowing down. Okay. Remember, all angles here are measured from the normal. And then finally with light, we looked at polarization. So this is kind of blocking light in one plane. And again, this is one reason we know that light travels as a wave. So again, polarization is unique to waves, right? Particles cannot be polarized. Okay. Polarization also explained 3D glasses. And then we're into modern physics. So this is the very, very new stuff that we just looked at. The first thing was the photoelectric effect, where you're taking a light with a certain frequency and shining it on a piece of metal. And what was discovered is that electrons are emitted. So you have these little electrons that are emitted from the metal. Okay? And what was kind of curious about this is that our thinking on waves could not explain what actually happened here. So the kinetic energy of the electrons was determined by the frequency. Okay? And this is something that the wave theory cannot explain. The frequency of the light wave should have determined something else other than the kinetic energy, right? But it was the kinetic energy. So if we graph this, there is what we call a threshold frequency, where that indicates to us how much energy those electrons will have to be emitted. Right? So below that threshold frequency, no electrons will be emitted, so there'll be no kinetic energy. Right? The number of emitted electrons actually had to do with the intensity, the brightness. So the number of electrons had to do with intensity. I'm just going to do capital I. And this is just a direct relationship here, right? The brighter the light, the more electrons were emitted. This did not indicate how fast they were going, right? That's the kinetic energy, right? And that's where the wave theory couldn't explain this. So we developed this new quantum theory, where the energy of those emitted electrons, we call them photons, particles of light, right? So these would be photons. The energy is related to the frequency of the light itself. Okay. Then we talked about models of the atom. So you should know the Rutherford model, right? And that he determined that the atom was mostly empty space, but had that dense positive nucleus. Right? The Bohr model is that planetary model, and we still use that today because that explains these energy level diagrams. Right? And then, of course, the cloud model is really what we know the model of the atom to be, but the Bohr model helps us visualize, right? And also explains spectral lines. So here's your